before I start telling how it works, I would like to explain where you can actually use it for. So clearly there is an operational segment, which has examples for extending operational windows, looking for slack tight periods. Are you able to launch an ROV or a diver already? You can look into tight towing maneuvers near platforms, oil platforms, keeping tension on the lines and sufficient speed in the corners. You can use it as an add-on to a DP system for difficult situations near platforms again, where GNSS coverage is poor and bottom track and current information can really help the DP system. And another one is, of course, proof of operational conditions to your contractor, or if it went wrong, for insurance purposes. The scientific segment, you can divide it in physics for coastal and oceanographic studies, for instance, for model calibrations. You can look into the biology departments of the scientific research companies, which can use this information for an explanation for local conditions. Is there any upwelling of nutrient-rich waters? And lastly, you can use it for mapping purposes, as vessel-mounted ADCPs can cover a wide area within a minimum amount of time. So you will have much more resolution with less or even no ADCP instrumentation on the bottom. You can think about tidal atlases for navigational purposes for harbors and harbor entrances. You can think about discharge calculation and discharge measurements on wider rivers. And secondarily, you can think about discharge of sediment transport using the speed of the water and the signal returned echo strength of the VM system. So how does it work? Well, it works basically the same as any other ADCP, which is stationary on the bottom, but then it's mounted upside down on a moving vessel. So clearly you need to correct for the ship's speed and motion and also the direction of the vessel. And that's where vessel-mounted acquisition software is designed, which will handle this and uses data from different sources to correct for the raw ADCP data. It needs heading and it needs a GNSS to georeference the data. And it can use its vessel velocity information to correct for the speed over ground from the vessel. There is also a possibility to use bottom track, which is coming from the ADCP itself. And this can also be used to correct for vessel speed and direction. And probably you will think, what is bottom track? We'll explain that in the next slide over here. Bottom track is a special ping transmitted in between of the velocity profiling pings. And it aims to detect the bottom, and it can also determine the depth. It uses the Doppler shift from the section near the bottom to determine the speed and the direction using its 4 beams. And as the bottom doesn't move, the Doppler shift information contains all the information about the speed and the direction of the vessel, which then can be used to correct the raw water velocity information from the ADCP itself. So what do you need? Obviously, you need as well a good and right vessel for the job, and you need to keep the survey conditions in mind. Besides that, of course, you need a proper broadband ADCP, vessel-mounted ADCP with bottom track. And with proper broadband, I need to explain a little bit about the broadband. Broadband is a Doppler processing technique that makes it possible to obtain better resolution in time and space compared to narrowband signal processing. And narrowband signal processing is the kind of Doppler processing which is in the somewhat older systems like the AWAC and the Aqueduct Profiler that we have. The difference between narrowband processing and broadband processing is that its accuracy is a factor of 3 to 5 times better in resolution and space and time. So over here you see a picture of narrowband information, and I would like you to show you the difference between narrowband and broadband. This is recorded at the same location and in the same time frame. So this is recorded by one instrument pinging narrowband. And over here you have pinging in broadband, which you can see it's much smoother. In the data itself is much smoother. What you need, in addition, you need an ADCP which pings fast to obtain as much as data in space or time, especially on a moving platform, of course. And you need the right frequency for your job. So on the left over here, you can see a 1 megahertz system, a 1 megahertz frequency, which has a range of 30 meters. And on the right over here, you will see a 500 kilohertz system, which has a 70 meter range below your vessel. And typically those are for coastal applications. For ocean applications, we have even lower frequencies, about 100 kilohertz, for instance, which provides you about 300 or more range. Well, as told, you need GPS for speed and georeference information. On a vessel, you also need a non-magnetic heading source, as the internal compass of the ADCP itself will not function properly. And today's GNSSs, they can also provide accurate heading, so they are dual heading GNSSs. Heading and speed heading and speed information should be merged accurately with the ADCP information, of course. So all the Ethernet equipment, they can work with P2P protocol, which is Ethernet timing protocol from the industry. And that makes it possible to merge the data from each sensor within the microsecond level. Mounting, of course, you need to mount your system quite sturdy, and that can be done on a non-permanent way, like over here on the right. And that's typically done over the side, pole mounted, or via a moon pool in the vessel. But you also have permanent mountings for ADCPs. And those are mounted in casings like blisters. And a blister is an external casing sticking beneath the hull of the vessel. And you also have a sea chest, which is again a casing, but then countersunk in the hull of the vessel. Thirdly, there is also an option to use a sea valve. And a sea valve is basically a huge valve which is able to retract the whole instrument through the valve. And this makes it possible to retrieve and to retract the instrument through the valve, and you can actually service it and clean it without making use of divers. Lastly, you need a compact processing unit to supply reliable, safe, and clean power to all your instruments connected. And you need a convenient way to connect all your instruments via the Ethernet. Acquisition software, that's of course also a need. So you need that to configure the instrumentation and also to visualize and store its data. Afterwards, there is post-processing software to select, filter, and export the data of interest, which you can then use after post-processing for reporting, of course. But before you start measuring with this equipment, you need to align your instrumentation properly. So basically on the vessel, you have 3 different coordinate systems. One is from the vessel, the second is from the GNSS instrument, or the heading instrument actually, and the third is from the ADCP. And most convenient, it's most convenient to align them all with the vessel's coordinate system. So how do you do that? Well, you start with the GNSS or the heading sensor on board, and nowadays they have heading output which can be plotted as a line on a navigational map. And when the vessel is moored parallel to a jetty or a quay, you can actually use that information and align that heading line with the jetty and the quay, of course. There are different ways to do this. You could also sail a line into the current and wind, avoiding any drift, and use the GGA information from the GPS. When there is no drift, then both heading informations should be the same. And lastly, you need to align the ADCP as well. Normally, typically they're installed with a mounting angle of 45 degrees off to provide you the best information as possible. So over here in the picture, you can actually see the GNSS course, which is the blue line, and you can see the bottom track course from the ADCP. And of course, they should be aligned properly. So you sail a straight line with good bottom track information, and you try to align those two by trial and error. And as you can see over here, we first aligned the bottom track with 45 degrees, and then afterwards we put it on the most recent GNSS location again. So if this is done, you're ready to go and survey. This means I'll hand over to Sikko, who will show you some results of vessel-mounted ADCPs.
Thank you, Herman. Been a little lazy today, so first going to show you an application which is we have been preparing in a very nice video. And this application is in the Netherlands, in Waddenzee, with a navigation channel which have difficulties with sedimentation. And the video will explain.
The challenge in this part of the Waddenzee is that the sea bottom is rising very quickly due to heavy sedimentation. And there's a navigation channel between the mainland and the island Ameland. Due to the meandering, it's getting longer in distance, and this means that the ferry takes longer to reach the island of Ameland. There will be more CO2 emissions, and there will also be an increase of dredging needed to keep the channel open. And there are plans at the moment to connect the village Holwert to this part of the Waddenzee by a 2-kilometer long channel. This might influence the sedimentation in the navigation channel towards Ameland, and that can also have an influence on the dredging work that needs to be done. The Signature VM series is specifically useful in this part of the Waddenzee because of its unique environmental circumstances with high sedimentation and high sediment concentrations over the water column. And the VM series provides us great insight over the whole water column and provides a lot of data that we can use for our model validations.
So the suspended sediment concentrations here in Holwert are very high. But the measurements showed us that not at all tidal stages the sediment concentrations are that high. Especially during high water, the concentrations are much lower. So if you use this water to fill the basin and to flush the channel with, the amount of sedimentation will reduce considerably. So the information that we gather during the measurement campaign will be used to calibrate numerical models and to improve the numerical models to be better able to predict what will happen in the future if Holwert SA will be constructed. And what will happen if the shortcut in the navigation channel has been executed. We hope that with these measurements we can optimize the dredging strategy, minimize the amount of dredging that should take place, and reduce our impact on this unique ecosystem.
Okay, this video is also available on our website. If you would have had any trouble watching it, then please go there. I didn't see any chats with complaints, so looks like good. We will be back on this this area and in this application in a later seminar and webinar also. Let's go down south. We're going to further south. Yes, Brazil. Our friend Diego has been giving a demo here last year in May, in a beautiful area around Sao Paulo in Santos. And if you look at the map on the top right here, Santos is here in Brazil. It's a nice estuary with a river outflow into the sea. A lot of exchange here, and we've been making measurements on these two tracks. I say we, but nobody asked me to go there, but let me explain it anyway. We're making two tracks, this one, on two different times on this very beautiful vessel. Nice and colorful vessel. So, Diego, thank you very much. We go to some results. This is the first track, and this is the track started here on the northern tip, and this is the end part on the southern tip. It was about 300 meters length. And what you see is nice little flow arrows here. These arrows indicate the depth average flow, so the average of the flow over the full water depth. And you see that that's pretty small here. This is just some tens of centimeters a second on the northern tip, and then here on the south it's even less. If you go to the more details, then we on the right, on the lower graph, we have the velocities, so the measured velocities, which is actually the speed of the water, how fast it goes. This is a graph which is in color depicting the speed, and the color bar on the right indicates what it is. So bluish is very close to zero, almost standing still, and if you go through yellow to red, then you are at 1 meter a second. The graph shows on the y-axis is the depth, so that's down to almost 20 meters here, and on the axis it shows the number of ensembles. So that's actually the number of individual measurements. Each of these is like 3 meters long, and altogether we're getting to the 300 meters. In the red line on the lower part, you will see the depth, how deep it is. That is measured with the vertical beam, as Herman just explained. And so then in color, you see the speeds. And that's funny here that on the lower layer in yellowish and even some reddish, the speeds are much higher. So those are going up to like 0.7 meters a second. That's the speed of the water. The layer above there, so 10 meters, a little up, that's bluish. So that speed is almost zero. And then we have a top layer where we have some speed again. Not as fast as here below, but again, 20 centimeters a second. So why is that? Well, if you look at the top graph with the flow direction, you can have a color bar, but now it's a different thing. It shows you the direction, starting at zero here and going all the way through to the north at 360. So that's around the globe. And then the depth axis again and the ensemble axis again, filling all 300 meters, matching to the lower graph. Now we see that the bottom layer is greenish, and greenish is here, 100 degrees. That's actually flowing inland, so upstream. That's the flow of seawater flowing into the estuary. While the top part is actually very different. It's more in this area, directions at 270 degrees almost, flowing outward. So what we see altogether is that we have a strong inflow of water on the bottom and a slower outflow of water on the top. It's very nicely visible in this kind of data. And in principle, you go from shore to shore, so you cover the whole area in one go, really. Now, we didn't use just a single track. We did another one. And it was about 6 hours later. And that track is a slightly different track. So the earlier one was here, from this tip to here. Now we started here, just a little bit east of this landfall, and it goes up to the same point. The end point is the starting point of the previous measurement. So this was 6 hours later, very different tidal area, tidal regime. And there we have, again, our flow vectors, where you see at the end point here, they're pretty strong, much stronger than we observed before. This is the average flow over the whole vertical. So this area is pretty strong, and we can step here, and actually the direction also changes here at the start. Yeah, and there's a little change in here. If you go to the flow velocities again, depth along the y-axis and the ensemble number, so basically distance along the x-axis. This distance is altogether almost 600 meters. So that takes a couple of minutes to make the trek. You see that the flow here on the lower part is actually quite small. It's again some tens of centimeters a second, where we have a little higher flow on the top. This goes up to 0.6, 0.7 meters a second. So that part up here, ensemble numbers 150 to 200, actually match the area near the end of the transect, all the way up here in the map. So you see a top layer which is floating, and a lower way which has some speed, and the lower part doesn't have much speed. If you go to the directional plot, which is the one on top, then you have the color bar again with the directions. You have an x-axis again, sorry, y-axis showing the depth, and then an ensemble number. And you see a slightly different picture. Here, the lower part, the flow direction is not really well defined. The flows are so small that the water doesn't flow in a certain direction really. The top part is much clearer, outward flow. Here, easterly outward flow. So we have an excellent top flow outwards, and that matches nicely those flow vectors. So for more scientific measurements or for governmental measurements, you would do that for a long time. You would do that for like 13 hours, a full tidal cycle, make these transects, maybe in 2 different tracks. So you have a nice image, you have time for these tracks, and you have 25, 26 nice consecutive images of the flow and the flow distribution in that cross-sectional area. And you can make nice flow maps and study what's happening.